Okay, so as you work through these, you got to see that when you double an angle, so if you take the sine of a double angle or the cosine of a double angle, it's not simply like multiplying the angle that you know by 2. So we have some more identities coming up today, and this is all referred to as the double angle identities, so it makes sense, I hope. So here's an example. I asked you to verify this identity. So here's the identity we're supposed to cover today, and I'm asking you to do it without any demonstration. And that's because everything today comes from our sum. Right? Our sum. We can say 2 theta is theta plus theta, right? 2 theta is, that's what I had you write here as the big hint. So if you write sine of 2 theta as the sine of theta plus theta, remember we're trying to establish that identity, so you got to put a straight line down there. You can't work one side, bring something from one side to the other. So if you use your angle formula, this is sine of theta cosine of theta plus sine of theta cosine of theta. So what do you have? You have, these are like terms. You got one sine of theta cosine theta and another one. So you got 2 sine theta cosine theta. So thus it is proven, right? That's how you show it. So that's our first double angle formula right there. You'll be using that throughout today. So there's one of them. Right. Then I wanted you, because I'm starting to realize that as we look at, say, double angle formulas, how would the graph of y of sine of 2 theta compare with, say, sine of theta? And how would the graph of 2 sine theta compare with the sine of theta? And how do they differ? So we could just bring up Desmos here and we could look at them, but I think you could tell me what's going on just from your knowledge of transformation. So how do these first two here, let's call them y1 and y2, differ from our regular sine of theta function? How do they differ? Yeah, Hazel? Right, this function, y1, has a horizontal compression or shrinkage. Its period is pi, because it's 2 pi divided by 2, which is pi. Whereas this one has a period of 2 pi. In some ways, I wish we could do transformations in 107 with trig, because it makes so much more sense. You can see it. So you can get, when you're looking at this function, from 0 to 2 pi, you get 2 complete cycles. Whereas here, you only get 1 cycle. So yeah, this one has been a horizontal compression, or shrink, right? Or shrink, however you like to think about it. And what about this one? How's that one differ? It's a vertical stretch of sine, right? So the period hasn't changed, just your amplitude has changed. Okay, so this is a stretch, vertical stretch. So you could almost imagine these two functions, the graphs, I hope, in your mind. You know what sine looks like? Doubling the amplitude, you go now from -2 to 2, but you're the same period. Every point gets stretched. And then sine of 2 theta would be the same shape, but you just get 2 of them in the same time period, or the same interval. Okay? All right, so let's take a look today at the rest of our identities. All right, so what's going on here? We're going to take a look at 2 special cases of the sum of angles identities called the double angle identities. We've already discovered one of the double angle identities in our preview exercises, smiley face. Let's list these identities and then let's prove them. Well, here's the one we've already shown and established. This was preview exercise number 3. So notice cosine of 2 theta is special. It has 3 different forms. 3 of them, 3 forms of cosine of 2 theta. It's 3 different ways you can write it. The nice thing is as long as you know sine of the sum of this, the sum of two angles for sine and the sum of two angles for cosine, you can derive all of these. You don't have to memorize all of them. You can just like we derived sine of 2 theta in the preview exercise, we can really do this one right now using the same technique. So let's do that. So if we want to find the cosine of 2 theta, we say, okay, the only thing I know how to do is take the sum of two angles, the cosine of the sum of two angles. So let's just call this theta plus theta. That's 2 theta. And let's use that addition identity. So we get the cosine of theta. Remember, cosine likes to keep to itself times the cosine of my second angle, which is also cosine of theta. My sine always changes with cosine. It's going to change to minus. And now it's sine's turn for each angle. Sine of theta times sine of theta. That equals the cosine squared of theta. Be careful, notice where I always put the square. You don't put it inside here with the theta. It's cosine squared theta minus sine squared theta. So this is our double angle formula, one of them for cosine. This is sort of the main one. This is like you know, I don't like assigning importance because you're going to use all three of them depending on what the rest of your either identity looks like or equation, but the other two come from this one. Okay, so this is like the biggie. And as you can see, you didn't need to know anything new to arrive at this. Any questions on how I got from here to here? Because it's good to ask it now rather than letting it sit there. Jackson? Because that's the identity. We established that last class if you look back, where that came from. But yeah, that's what the identity says. Sine, when you're looking at sine of two angles, the operation stays the same, but cosine, it switches to the inverse. Okay, any other questions? Okay, so how are we going to get these other two? Anybody have any ideas of how we can go from here to either this one? So look what's going on. Here we've got both sine and cosine in there, right? Here, it's all written in terms of cosine. And then the bottom one is all written in terms of sine. Anybody see any like strategy for how maybe we can go from this first cosine of 2 theta to this one, what we might do?
Sine squared.
So we want to make a substitution. We have to get rid of sine square, right? Because this next one's only in terms of cosine square. So what can we substitute for sine square? The Pythagorean identity tells you. Sine square is 1 take away cosine square. If we use our Pythagorean theorem. So all that, I would just keep this. This is your like big friend. Keep this at the top of your paper. So if I solve this equation for, say, sine square, I get cosine square is 1 take away sine square. So I'm just going to substitute that now into here. We'll keep the first one the same, cosine squared theta. And now I'm just going to make a legitimate substitution for sine square. It's 1 take away cosine square. Okay, there I go. And now I simplify this. So I get cosine square of theta minus 1 plus cosine squared of theta. I distribute that negative sign or the subtraction sign through. Hey, I got two like terms here. I got 2 cosine squared theta. Take away 1. So there's my second double angle formula for cosine. And I think you can see the writing on the wall for how we do the next one, hopefully. So in this first one, I substituted for sine squared theta with an equivalent expression. And now to get this final identity, I substitute for cosine square 1 minus sine square. So when I do that, let's go over here. Cosine squared theta minus sine squared theta. Now I'm going to pick on this one. So that, if I substitute 1 minus sine squared theta for that, take away sine squared theta, I get 1 minus 2 sine squared theta. So those are the three forms of the double angle formula for cosine. Again, if you're not good at memorizing things, all you have to do is just recreate it for yourself. But you'll probably all have these right alongside of your homework and stuff. And as you do this, you'll use these enough, you won't even think about them again. Or not too much anyway. Any questions on any of these three identities? All right, let's see how we can use them. So if sine of theta is 5/13 and theta is in the second quadrant, this is very similar to the problem we did from your lesson activity, right? Number 4, was it? 4 we just did? Okay. So, and this time let's make sure we're all doing it correctly and all the numbers and the multiplications right. All right. So sine of theta is 5/13. We're in the second quadrant. So what's cosine of theta going to be, positive or negative? Negative. So that's the first thing I think of. Okay, I'm in the second quadrant, so the cosine of theta is going to be negative. So that helps me to remember that anytime I write down a value for cosine theta, it's got to have a negative sign with it because I'm in the second quadrant. How am I going to find cosine of theta? Well, I'm going to use my Pythagorean theorem instead of the right triangle. I can sort of move beyond right triangle trig now because I got all these other great things in my toolbox. So sine square theta is 5/13 squared plus cosine squared theta equals 1. I square 5/13, I get 25 over 169 plus cosine squared theta. Now I might as well write 1 as a fraction with 169 in the denominator, so that's 169 over 169. And now I subtract 25 1/69ths from both sides, and I get 144 over 169. Oh, I like that because both of those numbers are nice perfect squares. So I don't have any radicals or irrational numbers in my answer. So the square root property tells me that I could have two possibilities here, plus or minus 12/13. But I remind myself, think second quadrant. So that means you're looking at cosine of theta is negative 12/13. Okay, so that's all you're going to need to find the exact values for each of these double angles. So what was sine of 2 theta? Oh, right, that's from my preview exercises. That was just double sine of theta, cosine of theta. So let's throw in our substitution now. Sine of theta is 5/13. Cosine of theta was negative 12/13. So I have my denominator is 169, and my numerator is negative 120 over 169. Done. I don't think that can be reduced. At least with my little divisibility rules I'm doing in my head, it doesn't look like it. Any questions on that? Okay, why don't you try the next one at your seat? Now you got 3 to choose from. Got 3 of them to choose from, so use whichever one you want. I should be using t here instead of theta. Okay, because that's what the variable is here. So I'm just so used to using theta. So sine of t plus cosine of t. And then sine of t, they look the same, minus cosine of t. Okay, that's how I factor the difference between two perfect squares. So sine of t plus cosine of t times sine of t minus cosine of t, all over cosine of t minus sine of t. Uh-oh, doesn't look exactly the same. Did I do that factoring right? What did I do wrong? Well, yeah, what's my first term here? So this should be cosine and sine. Cosine of t plus sine of t times cosine of t minus sine of t. There we go. Perseverance, stick with it. Make mistakes, you make mistakes, I make mistakes all the time. All right, so up here I just changed the order of each one of these. But again, recognizing how to go from that main form of cosine squared take away sine squared is the key here. And like I say, you'll always start to recognize these patterns as you do more of these. That's why it's so important to try to do as many as possible as your time allows outside of class. Now you see you have two factors in the numerator. You have a common factor in the denominator. There's your fancy form of 1. And so your answer is cosine of t plus sine of t. So that thing simplifies to just that sum. Okay. So factoring is one of those key ideas I put in. How do you prove identities? This is a situation where your factoring comes in handy. Way back in algebra, you're like, when am I ever going to factor? Oh, we'll be factoring your little fingers off for the next year in calculus. Okay, doing a lot of factoring. Questions before we go on to prove an identity?
How do you get to have better pattern recognition skills?
You do them over and over again. Really, I mean, there's no. I mean, you read your textbook, you look at some examples, and then you just have to it's like just diving in. You just got to try it, and if it doesn't work, you try something else, and then you get really frustrated and you throw it away, and then you try it again. I mean, I'm still looking at identities that I haven't done any trig identities. Well, a little bit when I used to help in the studio, but I haven't taught this class since 1991. So there's a couple that I can look at right now and I say, I wonder how I should start it. But I feel like, see, to me, it's like kind of like a puzzle. So I say, okay, let me try this. And if I'm getting somewhere, I stick with it and I try to make both sides look like the other. And I maybe work a little bit with one side and I start working on another side. If you look at it like a little puzzle, it kind of creates a little bit of that word that I'm not supposed to say, F-U-N, fun. All right, I know, I'm weird. All right, what can I say? So let's take a look. So I just want to show you how you use these double angle formulas to simplify. These two are directly out of your textbook. So I'm trying to get you to start reading and taking notes from your textbook. So I'm going to tell you, read your textbook and take notes on these two problems right out of your textbook. All right, but let's verify this identity because that's really where most of us, I think, need to do a little more work. So first thing you should do is put that big red line, change the color, that big red line down through the middle. We're not going to ever cross that red line. We don't add things from one side to the other here. So I don't even know, I don't have this identity in front of me anywhere. So I'm blind here. I don't know what to do either. So when I look at this, I say, what would I do? What would I do? Well, the right side's all cosine and the left side's cosine. That's good. What chapter am I in today? What section? Double angles. Is there any way I can write one of these like a double angle? Well, this isn't a double angle. It's just theta. So what could I do with the left side so I have a double angle in there? Hazel? And have it equal cosine of 3 theta? No, that would be a cosine square. Okay, any other ideas? Nick? Yeah, we got 3 thetas, right? What do we know how to do? We know how to do cosine of theta plus theta. We learned that on Wednesday. And today, what did we learn? Cosine of 2 theta. So why not put them together, the two identities? So that's where I'm going to start here. I'm going to say cosine of 3 theta is the same as 2 theta plus 1 theta. There we go. That's your 3 theta. Now I have the cosine of a sum of 2 angles, right? You could call the first one alpha and the first one beta if you wanted. So I'm going to have the cosine of 2 theta times the cosine of theta. Cosine likes to stick with like things. My operation changes to its inverse, and now I have sine 2 theta times sine theta. Okay, I'm going to remove that red line because I'm going to have to squiggle over it a little bit here. So I'm going to move the red line to over here like that. Okay. All right, now what do you think? I'm going to go with your ideas. Yeah, cosine of 2 theta. And we know sine of 2 theta as well, don't we? All right. The big question of the day is, which one do you use? Which of those 3 forms do you use? Because you got 3 different ways to write cosine of 2 theta, right? Well, Hazel, go ahead. Yeah, look, everything over here is in terms of cosine, right? I'm trying to get rid of the sines. So when I look at my 3 forms of the cosine of 2 theta, let's look at them. The main one looked like this. And the second one that Hazel's referring to looked like this. Right? So why not use that one? We'll substitute that right in here. Right? Notice it's being multiplied by cosine of theta, and so we're going to use a distributive property. So let's substitute this whole thing right here. We're going to take this whole thing, and we're going to replace it with cosine of 2 theta. Okay, all in parentheses, 2 cosine squared theta minus 1 times cosine of theta. So that's what that first term now looks like with the substitution. Okay. I'm not going to work on it at all. I'm just substituting in for cosine 2 theta. All right, we only have one form of the sine of 2 theta, right? There's only one form for this. So the sine of 2 theta, you will recall, is 2 times the sine of theta times the cosine of theta. So where I see the sine of 2 theta, I'm going to replace it with this expression. Okay. So I have a subtraction out here. I got to be careful. So I'm going to put my big brackets in now. So sine of 2 theta is 2 sine theta cosine theta times another sine theta. All right. This is where I like to put in, like when I used to teach order of operations, I would always have people just block out their terms, the pieces of an adding and subtracting problem, work on them individually. So now what do I have? I have something times a difference. So I use my distributive property here. I'm going to multiply cosine of theta times each one of those terms. So that gives me 2 cosine cubed theta. Woohoo! I've got a cube, and look over here, I've got a cube. I'm heading in the right direction. Minus cosine theta. So that's my first term, my first purple box. Now my second purple box here becomes, this is just all multiplication all the way across. So it's 2 sine square theta times cosine theta. Let's see. I don't know. How am I going to get rid of that sine squared theta? What? No. This is all one big multiplication problem here, right? 2 times sine theta times cosine theta times sine theta. No distribution. There's no pluses or minuses. This is one of the things I try to point out, and I'm so glad you said that, Hazel, because I have to point this out often in 107. This is the associative property. When you multiply more than two things, you can multiply any two at a time. Get the product and then multiply it by the next factor, get that product. So when I do this, I'm just rearranging. I'm just switching sine of theta over here, moving cosine of theta there, and multiplying sine of theta times sine of theta. It's the associative property. It's not the distributive property. Okay. Thank you for mentioning that. Yep, Jackson? Oh, are we okay up to here before we go to the next step? Anybody have a question that they can formulate if they have one? All right, so you want to let the cat out of the bag now? Yeah? Okay, so again, that Pythagorean theorem is going to come in. Look, we're almost there. We're almost home. Keep peeking on the other side. The other side has a cosine cubed. You got a cosine cube. You don't have 4 of them yet. And it's just in terms of cosine. So you've got to rewrite this so that you have something other than sine square. Okay, the first box I'm leaving exactly just as it is. I don't have any work to do on that box, that term. All right. But now where I see sine square, I'm replacing it with 1 minus cosine squared theta times cosine theta. All right, folks. You can do this in 2 steps or 1 step. If this is, again, the property I just mentioned to Hazel, who was brave enough to ask. This is just like 2 times 3 times 4. It doesn't matter which 2 I multiply first. So what I'm going to do is I'm going to put the cosine of theta in front along with the 2. I can do it in my mind without literally moving it, but for you, you should probably just move it in front like this. And now you can use your distributive property, but take this whole thing here, the whole coefficient that's out front, and times it by 1 and times it by cosine squared theta. Not forgetting that we still have this subtraction out here. So whatever I get, I'm going to put in parentheses. So I get 2 cosine of theta times 1 is 2 cosine of theta. Putting it all in parentheses because I got to subtract. Ooh, baby, I get minus 2 cosine cubed of theta. Oh, I'm almost there. I'm getting excited. Whew. So if I keep this box the same, ditto, I subtract both of these, what happens? I change the sign of each one. So I'm going to come in here now, and I'm just going to change the sign of each one. So that's minus 2 cosine theta plus 2 cosine cubed theta. I've got 2 cosine cubed theta here, 2 cosine cubed theta there. Gives me 4 cosine cubed theta. I check those off. And I have minus 1 cosine theta, take away 2 more cosine thetas, which is minus 3 cosine theta. And when you do that, you are a happy camper. I don't know what happened to my smiley faces for all my pens. They used to have little smile. Oh, maybe it's creative pens. There we go. So you're really happy. Yay. You proved your identity. All right, I got to do a quick equation for you before you, just to help you with this last little thing. Of course, you have a series of new equations you can solve now. I thought I might show you. Here we have cosine of 2 theta equals cosine of theta on your interval 0 to 2 pi. So it's saying what values of t will these two functions be the same. So what I did here in red is your cosine function. And this is compressed or shrunk, so you got 2 cycles of cosine in the blue on the same period. And where they intersect will be the solution. So you can see here you intersect here and you intersect there, and there's your answers. Graphically, there's your answers. How do we do it algebraically? That's the question. So any suggestions? Cosine of 2 theta equals cosine of theta, or t or x or whatever your variable is. If we solve an equation, that property we want to use often is setting everything equal to 0. That strategy comes up a lot because maybe we can get a square out of this and we get a quadratic in form, right? So let's see, cosine of 2 theta minus cosine of theta equals 0. So I am going to use right here, oh, I forgot to change my, I'm going to use the form of cosine 2 theta that has just cosine square in it. So it's 2 cosine squared theta minus 1, take away cosine of theta. And now with a little bit of rearrangement, I've got my quadratic term first, my linear term second, and my constant term. And now it's all set up to be factored. So I set up my factors, set them equal to 0. I've got a 1 and a 1, a cosine, 2 cosine here. Since my middle sign's negative, I'm going to put the negative sign there, plus 1 cosine theta. And then from there, you all have worked on doing these, I think, over and over, but let's quickly do it. Okay, let's do the one on the right-hand side because that's the quickest one to solve right here. When does the cosine of theta equal 1? I don't even have to do my arc cosine or cosine inverse because I know theta has to be what number? 0. There's one of my solutions. So if I'm starting my solution set, I got a 0 in there. Here we have cosine of theta equals negative 1/2. So I'm in the second and third quadrant for these solutions on this interval. So theta is in the first quadrant, I would be at pi over 3. The second quadrant, I would be at what number? 2 pi over 3. So theta is equal to that. Or the fourth quadrant, 4 pi over 3. So there are your 4 solutions. 0, 2 pi over 3, and 4 pi over 3. So that's a little bit of everything from section 7.3. I did keep out some stuff that I'll put into your that I've put into your activity for Monday. Let me just say one thing. What was that one thing before I saw Hazel's hand go up? Oh, please bring both your pink quiz and your quiz in that I've handed back to you on Monday, because there are a couple of things I want. Monday's sort of like, I'm calling it the trig catch-all day. So I wanted you to bring those in so we can talk about a couple of ideas from those quizzes. So please take the time to look it over, make some questions or notes so that if you have individual questions still, you can ask me on Monday. Okay, Hazel? Oh, it does say for all?